Hello, everyone. Today, Yang and I will talk about what's new in Kubernetes CSI. My name is Xing Yang. I work at VMware in the cloud storage team. I'm also a co-chair in Kubernetes SIG-Storage, along with Saad Ali from Google.
And I am Šafránek from Red Hat, and I am tech lead of SIG-Storage, together with Michelle O from Google. In this talk, we will introduce some new storage-related features we introduced as alpha, beta, or GA in the last Kubernetes releases. And we will cover only the most important ones from the storage backend and CSI driver perspective. Now, handing over back to Xing to talk about volume monitoring.
Thanks, Yang. First, I'm going to talk about this new alpha feature, Volume Health Monitoring. Without the Volume Health Monitoring, Kubernetes has no knowledge of what happened to the underlying volumes on the storage system after a PVC is provisioned and used by a pod. With this feature, the CSI driver can communicate with the storage system and find out what happens to the volumes and communicate back to Kubernetes. So Kubernetes can report events on PVCs or pods if volume conditions become abnormal. This feature includes two parts. There is an external volume health monitoring controller that is a sidecar deployed with the CSI driver to monitor volume health from the controller side. Kubelet also monitors volume health from the node side. Next, please. The external health monitor controller calls either list volumes or controller get volume CSI RPC and reports volume condition abnormal events with the messages on PVCs if abnormal volume conditions are detected. If a CSI driver supports list volumes and volume condition controller capabilities, it must implement controller RPC list volumes and report the volume condition in response. If a CSI driver supports get volume and volume condition controller capabilities, it must implement controller RPC controller get volume and report the volume condition in the response. There is also a node watcher component in the controller. If the enable node watcher flag is set to true when deploying the external health monitor controller, an event will be reported on the PVC to indicate that pods using this PVC are on a failed node when a node failure event is detected. The controller side volume monitoring has been alpha since 1.19 release. Next, please. When volume health was first introduced in 1.19, there was an external health monitoring agent that monitors health on the node side. In 1.21, we made a design change to avoid duplicate CSI calls. Kubelet already calls node get volume stats to retrieve volume metrics. In addition to that, it now also retrieves volume health condition through node get volume stats CSI RPC call and reports volume condition abnormal events with messages on pods if abnormal volume conditions are detected. Only CSI drivers with volume condition node capability support volume health monitoring in Kubelet. We added a new alpha feature gate CSI Volume Health in 1.21 to introduce this feature in Kubelet. Now I'm handing over to Yang to talk about FSGroup.
Thanks, Xing. FSGroup is a way how Kubernetes allows pods to access data on their volumes. For example, if a new ext4 volume is provisioned for a pod, then by default only root can write to it. And this is not useful because we prefer pods running as unprivileged users. FSGroup helps with that. It is an optional group ID in a pod security context, and Kubernetes will then run the pod with that FSGroup ID, and also it will change ownership of all files on pod volumes to be owned and writable by the group before starting the pod. Therefore, the pod can read, write anything on its volumes. It's nothing new. It has been in Kubernetes since forever, I think even before version 1.0. And all the ownership change is done by Kubernetes, not by the CSI driver on storage backend. There are a couple of issues with FSGroup. The first one is that it can slow down pod startup. If there are millions of files on a volume, Kubernetes will do the recursive change of all files on the volume every single time the pod starts. So in Kubernetes 120, we have a way how a user can opt out from this by setting a flag in pod security context. And ideally, the FSGroup will be applied only the first time the pod starts to get the right permissions. And the other starts will be fast without any FSGroup change. I won't dive into details here. You can check the link documentation. Important is, again, this doesn't introduce any change in CSI. The second issue we have with FSGroup is that sometimes it cannot be applied to files on the volume at all. For example, if the volume is an NFS share with root squash option, a kubelet that changes ownership of the files, it runs as root. And when it accesses the files on the volume with root squash option, this root user on NFS client side is translated to an unprivileged user on the NFS server side. And this user cannot change owner or permissions of the files. And therefore, Kubernetes int3 NFS volume plugin does not apply FSGroup at all. In Kubernetes, we have a list of volume plugins that don't support FSGroup, and NFS is one of them, and we don't apply FSGroup there. But for CSI, we don't know what kind of volume a CSI driver provides, and if it has something like root squash. So far, we had heuristics that tried to find out if a volume could be NFS. If a volume has access mode read-write once and FS type is set, then we assume it is not NFS and we apply FSGroup. You can see this heuristics is pretty ugly, even though it works well in most cases. So in Kubernetes 120, we have a beta FSGroup policy field in the CSI driver object. By default, it is set to read-write once with FS type, which is the current heuristics, because we can't change the default behavior. But we strongly recommend CSI driver vendors to set it either to file or to none. Most CSI drivers should set it to file, which tells Kubernetes to apply FSGroup recursively as it is doing now. And this should be used by the most CSI drivers. The option none is then for those special CSI drivers that don't support FSGroup. For example, when using NFS with root squash, or when the storage backend doesn't understand POSIX permissions at all. And the last issue we have with FSGroup is that some storage backends can apply it more efficiently than by recursively walking through the whole volume. For example, as a mount option, like Samba. This is currently work in progress. Check the linked pull request against CSI specification to see how we propose to pass FSGroup from Kubernetes to CSI driver so it can apply it as mount option. Please note, this is dedicated only to special CSI drivers that have those mount options or something like that. If your CSI driver just mounts a block device, then don't worry about this at all, and let Kubernetes change the permissions as it does today. Storage capacity tracking is a new feature that is in beta in Kubernetes 121, and it allows Kubernetes to see how much free capacity is available for dynamic provisioning and where it is available. For example, if your CSI driver provides storage that's local to nodes, then Kubernetes will track capacity for each node separately. And for example, it will know that node A has 100 gigabytes of free space for new volumes. And when it schedules a new pod with unbound PVCs, it will schedule it more likely to that node, so the dynamic provisioning can succeed there. How does it look on the CSI driver side? To enable capacity tracking, the CSI driver itself should report get capacity in its controller service, and then it needs to react to get capacity request and send correct get capacity response in the driver controller service. It will be called periodically by the external provisioner to query the available capacity. Depending on how the storage backend works, the external provisioner may be deployed in two modes. The first one is the one that we already know, and the external provisioner runs only once in a cluster in a controller pod. This is called with central controller. And the external provisioner will call the CSI driver with get capacity request for all the topologies it can find. So we assume that this CSI driver that runs in a pod with the external provisioner has some kind of API to query the storage backend for capacities of different storage topology segments. For CSI drivers that provide storage located on the nodes, there is a mode called without a central controller. In this mode, the external provisioner runs on every single node in the cluster, and it will query the CSI driver for capacity of a single node. Similarly, create volume and delete volume will be called on the right node. So the CSI driver doesn't need to synchronize the capacity or create volume, delete volume calls to some central component in the cluster. On Kubernetes side, the external provisioner creates CSI storage capacity objects, so the scheduler knows capacity of different topologies. And these CSI storage capacity objects are in the same namespace as the CSI driver to keep the cluster nice and tidy. And optionally, they could be also owned by the deployment or stateful set of the CSI driver. So if user uninstalls the CSI driver, this object will be automatically garbage collected by Kubernetes, and the CSI driver vendor doesn't need to clean them up during an installation. So you should not worry at all about this object. But what you should worry about is to set storage capacity flag in the CSI driver object. And this tells Kubernetes scheduler that the capacity is being tracked and it should be considered during scheduling. Another feature that we have is generic ephemeral volumes. And it is basically a better version of emptydir. If you know emptydir, it provides some scratch space for a pod to store some temporary data. The content of the emptydir volumes is deleted when the pod dies. So it's ephemeral and it's bound to a pod lifetime. Generic ephemeral volumes are exactly the same. They are bound to pod lifetime, but there is a real PVC and PV behind them. User can specify a PVC template in their pod as ephemeral volumes, and the template is instantiated when the pod starts, and it's deleted when the pod dies. But apart from that, it is just a regular PVC for Kubernetes, and especially for the CSI drivers, there is no change. Here is an example of such a pod. You can see a PVC template. The pod wants 4 GB of storage class. And anything that is allowed in PVC is allowed here in this template. For example, the pod could restore a snapshot of a volume or clone a volume or use a volume populator. So if generic ephemeral volumes are just regular volume PVCs and PVs for the storage backend, why I am talking about them here? It is important to distinguish them from the inline ephemeral volumes that we have in Kubernetes since Kubernetes 1.16. And the generic ephemeral volumes are on the left side, and that's what I just covered. They are something like emptydir, and the pod doesn't really care what it gets as long as it gets something persistent. So if it asks for 4 GB of some storage, it should get some writable 4 GB. And it expects some real storage backend that can provide those gigabytes. And it can be used with any CSI driver. On the right, there are inline ephemeral volumes that we introduced earlier in Kubernetes. They are still beta. And they provide some kind of fake volumes, like secrets. That's the use case you should have in mind when we talk about inline ephemeral volumes. They don't provide a real volume. They provide exactly what the pod wants. The pod must specify, for example, in secrets, if you use secret volumes, it must specify the secret name. So similarly, in the inline ephemeral volumes,
the pod must specify exactly what it wants, and then the volume appears in the pod. And these volumes are kind of read-only or not persistent at all, and they are fake. And what's important here, they require special CSI drivers, because this is Kubernetes extension of the CSI protocol, and you can't use a regular CSI driver for them. So please distinguish these two kinds of ephemeral volumes. They are both ephemeral, they are both inline in pods, but they have different use cases and they should be used differently. Now handing back over to Xing to talk about service account tokens.
Thanks, Jan. This pod service account token feature allows CSI drivers to impersonate the pods that they mount the volumes for. Thus improves the security posture in the mounting process without handing out unnecessary permissions to the CSI driver's service account. This feature is especially important for secret handling CSI drivers, such as the secrets store CSI driver. Since these tokens can be rotated and short-lived, this feature also provides a way for CSI drivers to receive node publish volume RPC calls periodically with a new token. This feature adds two fields in CSI driver spec. They are token requests and request republish. Token request struct has two fields, audience and expiration seconds. Audience is the required field. It refers to the recipient of the token. Audiences should be distinct, otherwise the validation will fail. If it is empty string, the audience of the token is the API audiences of Kube API server. Expiration seconds specifies when the token will be expired. The second field in CSI driver spec requires republish is optional. If it is true, node publish volume will be periodically called. When used with token request, the token will be refreshed if it expired. Node publish volume should only change the contents rather than the mount, because container will not be restarted to reflect the mount change. If token requests is set in CSI driver, the token will be bound to the pod that the CSI driver is mounting volumes for and will be set in volume context in the node publish volume RPC. If CSI driver doesn't find token recorded in the volume context, it should return error in node publish volume to inform Kubelet to retry. There is a feature gate, CSI service account token, which is enabled by default in 1.21 because now the feature is beta. Next, please. As mentioned earlier, the secret store CSI driver has implemented the pod service account token feature. I also included other resources here for your reference. Next, please. So now I'm talking about the volume snapshot feature. This feature moved to GA in 1.20 release. It includes CRDs and other common components, such as the snapshot controller and a validation webhook. We strongly recommend Kubernetes cluster distros to install these components because they are independent of CSI drivers. There is an external CSI snapshot sidecar that should be deployed together with the CSI driver. The implementation of create snapshot, delete snapshot must support idempotency. List snapshots is only used for pre-provisioned snapshots to validate the snapshot handle provided in the volume snapshot content. So list snapshots is only called with the snapshot ID as filtering to query a specified snapshot. Next, please. CSI spec is intended to support all storage systems. However, there are design challenges as storage systems don't behave exactly the same way. In the case of snapshots, there are two different snapshot semantics. For some storage systems, a snapshot is locally stored alongside the volume on the primary storage. It is usually quick to cut a local snapshot like that. For other storage systems, after a snapshot is cut, it will be uploaded somewhere in the cloud. This upload process takes a long time. For this reason, we have a ready-to-use flag in volume snapshot status. If a snapshot does not need an upload, CSI driver will return from create snapshot right after the snapshot is cut and set ready-to-use to true. If upload is needed, CSI driver will return from create snapshot after the snapshot is cut, but set ready-to-use to false. Snapshot controller will keep calling create snapshot to check the status until ready-to-use is true, which indicates upload is complete. Both snapshot semantics are supported and conform to CSI spec. Another thing I want to mention is that in Kubernetes, volume snapshot and PVCs have independent life cycles. This means Kubernetes will not block a PVC from being deleted when there are still volume snapshots on it. However, for some storage systems, volume cannot be deleted when there are snapshots. In the CSI spec, we have mentioned that CSI driver can return failed precondition gRPC error code to indicate that the volume could not be deleted because it is in use by another resource or has snapshots, and the plugin doesn't treat them as independent entities. Another solution recommended by the Kubernetes CSI team is to implement reference counting in the CSI driver to allow PVC to be deleted when there are snapshots and delete the volume on the storage system only when all snapshots are deleted. Next, please. Now I'm going to talk about CSI Windows. CSI Windows is targeting GA after the 1.20 Kubernetes release. There are challenges for CSI drivers to work on Windows. Windows containers are not privileged. However, CSI drivers need to perform privileged operations such as mount and unmount. The solution is to have a privileged proxy binary named CSI proxy that runs as a native Windows process on the Windows nodes, configured as a Windows service. The CSI proxy will expose an API through gRPC over a named pipe for executing privileged storage-related operations on Windows hosts on behalf of Windows containers like CSI node plugins. CSI proxy API groups include the disk, volume, file system, SMB, and iSCSI. Next, please. Only CSI node RPCs need to be implemented by CSI drivers to support Windows. In this diagram, we use CSI call node stage volume as an example to explain the interaction between Kubelet, CSI plugin, and CSI proxy for mounting a volume. After the node plugin receives a CSI RPC call, it makes a few calls to CSI proxy accordingly. As a result of the node stage volume call, first, the required disk is identified using either of the disk API calls, list disk locations, or get disk number by name. If the disk is not partitioned, then the partitioned disk from the disk API group is called. After that, volume API calls such as list volumes on disk, format volume, and mount volume are called to perform the rest of the required operations. Similar operations are performed in case of node onstage volume, node publish, unpublished volume, node expand volume, and so on. I listed some additional references here for CSI Windows. So those are all the new features that we want to talk about today. Next, please. Here are some sessions at KubeCon's storage track that will happen in the next few days. Check them out if you are interested. This is the end of the session. Thank you all for attending.